now that we have an understanding of what a differential equation is, we're going to look at how we actually solve differential equations. And we're going to first start off with first order differential equations. And again, these are ODEs, ordinary differential equations. First orders means we're only looking at the first derivative. And so we're going to be dealing with how do we solve these. Before we actually look at how do we actually physically solve them, we're going to look at what the solution curves look like. You can actually look at what the solution is without actually knowing what the solution is algebraically by looking at what we call direction fields. So that's what we're going to look at, is how do we actually look and visualize the solution curve. So remember, a first order differential equation would be dy dx equals something. That something is, remember from Calc 1, dy dx is the slope of the tangent line at some point. So a direction field is the point slopes at many points. So we're going to plot these points at many different, we're going to plot the slopes at many different points in our direction field. So remember, dy dx again is some function, and this is what we call the slope function. So as an example, I'd like to sketch the graph of dy dx equals e to the x times y squared. We are going to use technology for that, but just to show you kind of what this means and what it means to do a slope field, we're going to actually make a table of values. And my table of values will be just picking x values and y values, and then finding the slope, the derivative. So let's pick x equal to 0 and y equal to 0, because the domain of this is only real numbers, so we can pick anything we want. So we'll start with 0, 0. It's always nice. So if I put 0 in here, of course, for x and y, we get e to the 0, which of course we know is 1. Let's pick x equal to 0 and y equal to 1. If x is 0 again, 0 times 1 is 0, so e to the 0 is still 1. And in fact, anytime x is 0, you're going to get 1 for the derivative. So let's pick x equal to be something different. Let's pick x equal to maybe 1. Now let's pick y equal to 0. Well, now again, same thing. If y is 0, you've got e to the 0, which is again is still 1. So anytime y is 0, you will also have a slope of 1. So those are kind of boring. So let's pick something totally different. Let's pick x equal to 1 and y equal to 1. Then we're going to have e to the 1, which of course is about 2.7. I'm going to keep going with this, pick a few more points. So let's pick x equal to 2 and y equal to 1. If x is 2 and y is 1, then we have e to the second. And e to the second, I have to admit, I don't know what that one is by heart. So I'm going to have to go ahead and pull out my calculator, type it in my calculator, and I get about 7.4. Let's pick, if x is ever, well, let's pick x equal to 2 and y equal to 2. Then if I pick x equal to 2 and y equal to 2, then we would have 2 times 2 squared, so 2 times 4, or 8. So I'd have e to the 8. And again, I don't know what that is, so let's find out what that is on our calculator. And that's like 2,980. So that's really, really big. So I think maybe when we want to pick x equal to 0 and y equal to 2, I'm sorry, x equal to 1 and y equal to 2, that's what I wrote. And so that would be 2 squared would be 4, and e to the 4 is 55, let's say. Sorry. All right, so we could keep doing this, but we're just going to get really, really big numbers. So let's actually think about plotting this up. So our x's and y's only range from 1 to 2. We didn't give them really big values here. Now the slopes are where we're having some importance. When x is 0 and y is 0, in other words, we're at this point right here, my slope is 1. So we're going to be heading up to here. We could head all the way up to there, but we don't need that the slope that long. We don't need the line that long. So we could just draw a little arrow kind of heading in that direction. There's your slope of 1. Again, anytime y is 0, you're going to get a slope of 1. So we can know we can do those. Anytime x is 0, we're also going to get a slope of 1. Now let's get the other points on there. So when x is 1 and y is 1, in other words, we're at this point here, we have 2.7. So it's going to be a bit steeper, maybe something like that. Again, they don't have to be very long lines. It's just trying to give you an idea of the general shape. When x is 2 and y is 1, we get about 7.4. So that's even steeper. When x is 2 and y is 2, we get incredibly steep. So it's almost vertical line there. Not quite, but I mean, in this scale it is. When x is 1, oh, I'm sorry, I did the wrong one. That's the 55. When x is 2 and y is 2, then it's even steeper. So you can get this idea of what it looks like. We're going to really use technology for this to get a really good idea, but now what you can do is kind of draw along and follow this line and get your solution curve and see what the curve looks like. We're going to go ahead and again use technology. If you're in my class, you've got a Canvas shell and you can go into there, you go to web links. I have several different applets that will do slope curve fields. You can search for them online. Just Google slope field applet and you'll get many up there. I happen to like the Bluffton University site. I like this one a lot. And this is what the site looks like. And it gives you, you can do one ordinary differential equation or a system and so forth. So we're going to go ahead and just do the one. We actually have e to the x squared times y squared. Let's put that in parentheses. And then you hit enter and it draws it for you. So you can now see this is the same slope field we had before. It's just a little bit more detailed, more values are graphed. I'm going to go ahead and snip this so I can get a picture of it and put it where I'm working. So I'll snip this. Yeah. Let's try it again. So I'll snip this. I'll copy this and I will put this in my notes. And there's my slope field drawn with technology. The nice thing again, what I can do with this now is I could actually think about picking some point, some initial point. There's my initial point. I'm going to now follow these tangent lines. So if I follow along here, I can see that I'm kind of thinking about these tangent lines, following along here. I'm getting steeper, I'm getting even steeper, and then I'm getting really, really steep. Not the vertical asymptote necessarily, but just really steep. I could also come along towards the negative. You don't always have to go in the first quadrant. So I can go into the third quadrant here. Again, I'm following this along. I'm coming down, and then I notice it's a little bit less steep. And it looks like we're kind of heading off in that direction with kind of a horizontal asymptote. It looks like a bit there. And we can see what that looks like. And you can do this for any point. So you can pick any initial point that you want. Pick an initial point over here. You can come along, follow along, think about what that slope is doing. It's getting really steep there. It's coming down. And then it's kind of going off on my horizontal asymptote direction. The website will actually draw these for you. So you can actually just click a point that you'd like to draw, and there will draw that in for you. Click another point, and it draws them all in there for you. And so you can see what's happening with these. And that gives you an idea of what the slope, what the solution looks like. It gives you a visual idea of what your solution looks like without actually knowing what it is and solving that differential equation. All right, so that's slope fields or diffraction fields. They got both names. I now want to talk about one other concept here that we can still do visually without actually solving anything, without actually finding an analytical solution. We can still do a visual solution. It's still a solution. It's just not analytic. And we're going to talk about a thing called autonomous first order differential equations. What we mean by autonomous is that the independent variable does not appear in your differential equation. In other words, your derivative of y with respect to x is just a function of y. There's no x in this function at all. So your right-hand side of the equation has only y's in it, or it's just a function of y. A good example of this is the rate of change of a population over time. When you have continuous growth and you have no limiting factors, it's going to be k times p. Notice time is not involved in this equation. An example of a non-autonomous, this is actually for a circuit equation. Q is your charge, and the change in charge over time is equal to 1 over the resistance, which is R, times E of t, which is your voltage source, minus 1 over R times C, which is your capacitor, times again your charge. Notice E of t is involving time. So this E of t, which is your voltage source, is involving your independent variable. So this one's not autonomous. What I want to do is I want to look at how do we solve these. So remember from Calc 1, the derivative of y with respect to x is usually we set it equal to 0 to find those critical points. So that's what we're going to do. We're going to find those critical points. We're going to find out when does the derivative equal 0. That C is your critical point, or we can call them our equilibrium points, or sometimes called a stationary point. Y of C equals C, y of x equals C is what is a solution to your equilibrium solution. So this would be, once you find out what that C is, you can now get your y of x equals C is your solution, or what we call the equilibrium solution. So let's go ahead and do an example of this. I want to visualize this just a little bit before we get into it. So let's go ahead back to here. I'm going to go ahead and turn off, get rid of my curves, because I don't want them on there when I draw this. My function we're dealing with, I've got to go back and make sure, is y squared minus y. So we've got y squared minus y is my function. Hit enter, it'll draw it. And what I notice here is it looks like, oh, y squared, I forgot the square, oops. Y squared minus y, there we go. Okay, now we're better. And it looks like, if I look along here, it looks like these slope fields, these slopes are coming down, these look like they're coming up. So it looks like there might be an equilibrium solution right here at 0. It also looks like we're coming down to some value here and maybe coming up to some value. So it looks like maybe 1 is another 1. So it looks like we can see from the slope field what our equilibrium solutions are. Let's go and try to find it. So now what I'm going to do is say, well, let's just set this equal to 0. So set this equal to 0. And so we've got y squared minus y equals 0. Factor that. So y equals 0 and y equals 1. So those are my two critical points. And those are my two equilibrium points. And my equilibrium solutions are y equals 0 and y equals 1. At least that's what it looks like. It looks like the equilibrium solutions are y equals 0 and y equals 1. So now what I'd like to do is I'd like to think about what's happening in these different intervals. So what is and that's what we did with our derivatives when we were in Calc 1, is we looked at what is the derivative on either side of these intervals. So let's look at from negative infinity to 0, what is the sign of that? So remember, our derivative is y squared minus y, or y times y minus 1. So that was our derivative, y squared minus y, or y times y minus 1. If x is less than 0, I'm sorry, if y is less than 0, the y is negative, y minus 1 is negative, and a negative times a negative is, of course, positive. If we're between 0 and 1, y is now positive, but y minus 1 is still negative, so we're going to have a negative. If we're bigger than 1, then y is now positive, and y minus 1 is also positive. So you're going to have a positive number. And remember from Calc 1, you can tell me that when the derivative is positive, that means your function is going to be increasing. And if your derivative is negative, then your function is now decreasing. And again, we're going to be increasing after that. So I can actually kind of visualize this with what we call a phase portrait. And a phase portrait, it's just kind of think of it as your y-axis. You're going to have some point here 0, your point here 1. Below 0, you were increasing, so we can think of drawing an arrow to come up to 0. Between 0 and 1, we were decreasing, so we think of having this arrow that goes down to 0. And above 1, we can think of having a positive. And what this does is it actually allows me to think about what we call a phase. This is actually called the phase line. So this part here is just your phase line. But from that, I can get a phase portrait. So I can actually think about from this information what this function looks like. So let's just draw an axis here. We'll draw a coordinate plane. Here we have 0, here we have 1. We know 0 is one of our equilibrium solutions. 1 is another one of our equilibrium solutions. So you can think about having these two solutions curves here. They're horizontal lines. This is 1 and this is 0. So you can think of having those horizontal lines. And then we can think about what's happening in here. So thinking about this for a moment, we now have these two horizontal lines. We actually can think of this as being a whole space here. Down here is one space of our plane. It's just a rectangle, so we can call this R1 for some space. Between 0 and 1, again, we have another rectangle, another space of our coordinate plane, so we can call this R2. And above 1, we have another space we're going to call R3. So we have some properties we're getting here. Let's think about these are. These are kind of conclusions about the situation of these autonomous functions. We're going to suppose just for ease that there's only 2 critical points, but you can have multiple critical points. We're going to also suppose that C1 is less than C2, just for convention's sake. We already know that the graphs of the y of x equals C1 and y of x equals C2 are horizontal lines. We just plotted those. We can see those. We also happen to know we get these sub-rectangles where we divided the full coordinate plane up into these sub-rectangles. Now let's talk about what happens if y goes through some point, and that point happens to be in one of these rectangles. So let's just say for a moment, coming back to my phase portrait, if I'm taking some point here, down here in R1, in this first rectangle, I notice first off that the function is increasing here. So I notice I'm increasing function, and I know kind of that I'm going to see that we're going to be coming up here, and we're not going to be leaving this axis. We're going to be coming up and kind of going along here. So we know that we're not going to cross this horizontal line of y equals 0. So in fact, that's what this next property says, is that y of x is entirely in R1. Because we can't suddenly change, we already know that we're increasing in this first rectangle. So we can't just suddenly jump out of here, because we also know we're decreasing in the second rectangle. So we can't think of jumping from R1. We're not going to be coming up here, increasing up here, and leaving this rectangle. We're going to stay in this rectangle. We're not going to be doing that. We're going to be coming up here, and we're going to be staying along this rectangle and kind of following along that line. So these are some more properties that we just saw. We can't change signs in the rectangle, subrectangles. We already knew that because that's how they were created. We also know it's monotonic. We know that we're only increasing that interval. So we know we're not going to be changing from increasing, decreasing. So we're only going to be monotonic. If y of x is less than C1, then as x goes to infinity, or goes to negative infinity, then the y of x goes to that C1. And we just kind of solve that. I was less than C1. I know that as x goes to infinity, in this case, I'm going to be heading towards this C1. Think of this as a horizontal asymptote that I'm heading towards. I'm heading to that value. I know I'm heading towards it as x goes to infinity because we're increasing. No other reason. There's nothing special about going towards it as x goes to infinity. It's just because we're a positive slope and because we've got an increasing function. If we're between, C1 is between, or y is between C1 and C2, then as then y will go to C1 and y will go to C2 as x goes to infinity and negative infinity. So looking up here, what that means again is if I pick some point here that's in R2, we are decreasing, so we're not going to change from being monotonic. So when we're coming decreasing from that point, we know we're not going to be able to leave here, so we must be having to come closer and closer to this line. If we went the other direction, headed towards negative infinity, we know we can't leave here. We know we're going to be monotonic. We know we're only going to be increasing. So we know we can't cross that line because we know we can't get out of here. So we must be heading towards it in an isotonic way. And of course, the last one is if you're bigger than C2, then you're going to head to C2 either as x goes to infinity or x goes to negative infinity. In this case, if I'm up here, we are increasing, so we know we're going to be going upward from here. We know we got to be increasing, but we know that as x goes to negative infinity, we're going to be heading towards that line, y equals 1. So those are our properties. Let's do one more of these kind of examples. We'll do another one. We're going to do a phase line and the phase portrait. Our differential equation is dy dx equals y squared minus y cubed. Again, I'm going to set that equal to 0. So y squared minus y cubed equals 0. So factor out of y squared, you get y minus 1 equals 0. Again, I'm going to do my phase portrait first, my phase line first actually, and the phase line helps me get the phase portrait. The phase line is just that axis, just the y-axis. I know y equals 0 and y equals 1 are my two critical points. Again, you can have multiple critical points. I'm just showing you some examples, I only have 2. So I know I have 0 and I have 1. I know I have horizontal lines at 1 and 0. So I'll draw those in there. Actually, that would be for the phase portrait, so I don't want those just yet. All right, so we're just going to find out whether or not we're increasing or decreasing. So if x is less than 0, I'm sorry, if y is less than 0, if we're down here in this part of the plane, this part of our line, if y is less than 0, y squared will be positive. Y minus 1, we're going to take a negative number and subtract 1 from it. You're still going to get a negative number. So positive times the negative is negative. So we know we're going to be decreasing in that range. From 0 to 1, we know that y squared is positive. 1, if I take like 0.5 minus 1 is, oh, that's why I messed up. Oh, sorry, I'm messing up. I apologize, I didn't factor correctly. It's 1 minus y. All right. So that means I'm going to take 1 minus a negative number. I apologize, didn't mean to mess that up. Helps if you factor correctly, so always make sure you check your factors. So if I'm again less than 0, y squared is positive, 1 minus a negative number is going to give you a positive number. So in fact, we're going to be increasing below 0. Between 0 and 1, again, y squared is positive. 1 minus y, so 1 minus 0.5, 1 minus 0.1, that'll be a positive number. Positive times positive, it's still going to be increasing in this realm. And then from 1 on up, y squared is still positive. 1 minus y, if I take a 1 minus a number bigger than 1, I'm going to get a negative number. Positive times a negative is negative. So I know I'm decreasing. So there's my phase line. Now we can get our phase portrait. So again, think of it as here's your 1. Think of this as your horizontal line at y equals 1. Here's your 0. Think of again your horizontal line at y equals 0. And now I can draw my phase portrait in. So picking a point down here, again, you don't care where you pick the point. You just need a point to kind of start with. We know we're going to be increasing. So I'm increasing, going to that point, and then I'm increasing. I'm going to head towards this line. So it looks something like that. So there's what that one looks like. Here, let's pick a point here. I know we're going to be, again, increasing. So we're going to increase, but we're going to come along that line. Then we're going to increase, increase, and then we're going to come along that line. And then if we pick a point above here, we know we're going to be decreasing. So we know we're going to be coming down to that point and then coming along this line. And there's what your phase portrait looks like. Let's go ahead and just look at the slope field of this. So I'm going to go ahead and do y squared minus y cubed. Take a look at this graph. And you can see, again, you can see nicely with your slope, your direction field or slope field, that you have these horizontal equilibrium solutions. Here's my equilibrium solution at 0. Here's the one at 1. And I can see that if I'm up here, I do get a line that's going to come down and come along there. If I'm down below 0, I'm going to have a line that comes up along there. And if I'm in between, I'm going to have a line that comes up and goes along there. So I can still see that's happening and what's going on with this. This one was, the first one was a little strange because of just graphical, doesn't always work perfectly. So we can draw some others and we can see that that's happening. And that's how we can visualize our information.